Welcome back to another lesson in physics. Today we're going to be studying the electric force. The electric force is a quantifiable force. It is governed by Coulomb's law. Coulomb's law shows the relationship between the electric force, the two charges, Q1 and Q2, and the separation distance between the charges. The electric force, like all forces, is a vector quantity with units of newtons. To determine the direction of the electrical force, you use the rule of fundamental charge. Opposites attract, likes repel. So as an example, I have a particle A and a particle B. They have like charges, and so they repel. And this vector here represents the force from B on A, which is going to be equal and opposite to the force of A on B. Here I have a particle C and a particle D. C is positively charged, D is negatively charged. And so the force by C on D is going to be equal and opposite to the force from D on C. And the two charges attract because they're opposite charge. The larger the charge, right here in Coulomb's law, the greater the electrical force. The larger the separation distance, the less the electrical force. And so Coulomb's law is directly related to the charge of the particles and inversely related to the separation distance. Coulomb's law holds true for any charged particles, and when you're looking at the distance, you take the distance from the center of the particles. So here would be the separation distance for these charges, and here the separation distance would be from the center of C to the center of D. So Coulomb's law holds true for any point charges or for any spherical charged objects where the charge is uniformly distributed. Coulomb's law says that the electrical force is equal to charge 1 times the charge of particle 2 divided by the separation distance squared, and all of that is times a proportionality constant called K, where K equals 9.0 times 10 to the 9 Newton times meter squared per Coulomb squared. So let's say that you have an electrical force, but then the charge becomes twice as big. So if you double Q1, then the electrical force is doubled. This time, let's say that you double Q1 and you triple Q2. Then it would be 2 times 3, which is the electrical force would go up by a factor of 6. Let's say that you bring the charges in twice as close. So you half the distance. And so 2 times 2 is 4, so the electrical force becomes 4 times stronger. And that's what it means to have an inverse square law. The inverse square law says that the electrical force is related to the distance square, and the relationship is inverse. So let's try a couple more examples to see if you really understand what it means for something to be proportional to the inverse square of it. So this time, let's take the particles and spread them out a factor of 3 times farther apart. So then you would do 3 squared, which is 9, and since you're making them farther apart, the electrical force would go down by a factor of 9. Large is such a large quantity, we often express it as 1 Coulomb equals 10 to the 6 microcoulombs. So you're going to see charge being expressed in microcoulombs or nanocoulombs. 1 nanocoulomb Coulomb would be 1 times 10 to the negative 9 coulombs. Again, I want to repeat myself and say don't worry about the sign of the charge until the end of the problem. And so you'll see that charge has absolute value signs around it. And so you're not worried about whether it's positive or negative until the end of a problem and when you look to see if it attracts or repels. So the electrical force is going to be the same for Q1 and Q2. Coulomb's law can be compared to Newton's universal law of gravitation. It's the gravitational force law discovered by Sir Isaac Newton. So if you'll notice, Newton's law of universal gravitation looks a lot like Coulomb's law. The universal law of gravitation says that the force of gravity is proportional to the product of the mass 1 and mass 2. And it's inversely proportional to the distance squared. So both Coulomb's law of electric force and Newton's law of gravity show that the force is proportional to the products of the quantity that causes the force, and that the forces are inversely related to the distance between the quantities that cause the force. How are they different? Well, there's a few things. First, to make note, the gravitational force is due to the masses of the object, and the electric force is due to the charges. You'll also take note of the proportionality constant in the Coulomb's law. It's very large. It's on the order of 9 billion. And so you know the electrical force is going to be a very strong force. Whereas with Newton's universal law of gravity, the gravitational constant is very tiny. It's on the order of 6.6 trillionths. So a very, very, very tiny number, almost practically zero. And so that makes the gravitational force a very, very weak force. And you only start to notice the gravitational force when these masses become huge, like the masses of the planets and the sun and other stars in our universe. And also, don't forget that gravity is only attractive, so you don't have to worry about one of these masses ever being negative, whereas the charge could be positive or negative because the electrical force can be both attractive and... All right, thanks for tuning in. Today you got to learn a little bit about the electrical force. We see that the electrical force is proportional to the product of the charges and inversely proportional to the distance squared. This is very similar to Newton's universal law of gravity. And in our next video, I'll be showing you how to use the electrical force to compute some problems and solve some problems that involve the electrical force. So stay tuned for that video.